Hello and welcome. In this video, we will explore several key rules of differentiation that are essential for the IB mathematics analysis and approaches higher-level curriculum. By the end of this session, you will be able to, first, use the chain rule to differentiate composite functions. Second, apply the product rule to find the derivative of a product of two functions. And third, use the quotient rule to differentiate a function that is a ratio of two other functions. These rules are fundamental tools that will allow you to differentiate a much wider range of functions than you could with just the basic power rule. Let's begin with the chain rule. This rule is used to differentiate composite functions. A composite function is a function of a function. For example, if we have a function y equals g of u, where u is itself a function of x, say u equals f of x, then y is a composite function of x. The chain rule provides a way to find the derivative of y with respect to x. The rule states that the derivative of y with respect to x, dx, is equal to the derivative of y with respect to u du multiplied by the derivative of u with respect to x dx. This can be thought of as differentiating the outer function with respect to the inner function, and then multiplying by the derivative of the inner function with respect to x. A very common application of the chain rule is for functions of the form y equals f of x raised to the power of n. The derivative is n times f of x to the power of n minus 1, multiplied by the derivative of the inner function, f prime of x. Let's work through an example to see this in action. Consider the function y equals the quantity x squared minus 2x, all raised to the power of 4. We want to find the derivative, die. First, we identify the outer and inner functions. The outer function is something to the power of 4, and the inner function is x squared minus 2x. Let's define u as the inner function. U equals x squared minus 2x. This means our original function can be written as y equals u to the power of 4. Now we find the derivatives du and du dx. The derivative of y with respect to u is 4u cubed. The derivative of u with respect to x is 2x minus 2. Next, we apply the chain rule formula. Die dx equals die du times du d, which is 4u cubed times the quantity 2x minus 2. The final step is to substitute our expression for u back into the equation. Replacing u with x squared minus 2x, we get our final answer. Die/dx equals 4 times the quantity x squared minus 2x cubed times the quantity 2x minus 2. Notice the brackets around 2x minus 2 are essential, as the entire expression is multiplied by 4x2 and 2x3. Let's try another example, this time involving a square root. We want to find the derivative of y equals the square root of 3x minus x squared. First, it's helpful to rewrite the square root as a power. So y equals the quantity 3x minus x squared, all to the power of 1/2. Now we identify the inner function, u. Let u equal 3x minus x squared. Then y equals u to the power of 1/2. Next, we find the derivatives du and du dx. Using the power rule, die/du is 1/2 u to the power of negative 1/2. The derivative of u with respect to x is 3 minus 2x. Now we apply the chain rule. Die dx equals die du times du dx, which is 1/2 u to the power of negative 1/2, times the quantity 3 minus 2x. Finally, we substitute u back in and simplify. Replacing u with 3x minus x squared, we get 1/2 times the quantity 3x minus x squared to the power of negative 1/2, times 3 minus 2x. We can rewrite this with a positive exponent and a square root in the denominator to get our final answer. Now let's move on to the product rule. This rule is used to differentiate a function that is the product of two other functions. Suppose we have a function f of x that is the product of two functions, u of x and v of x. A common misconception is to think that the derivative of the product is the product of the derivatives. Let's quickly see why this is not true. Consider f of x equals x squared. We know the derivative is 2x, but if we write f of x as x times x and apply the incorrect rule, we get 1 times 1, which is 1. This is clearly not 2x, so we need a different rule. The correct rule is as follows. The derivative of f of x is the derivative of the first function, u prime of x, times the second function, v of x plus the first function, u of x, times the derivative of the second function, v prime of x. In other words, it's the derivative of the first times the second, plus the first times the derivative of the second. Let's apply this to an example. Let's find the derivative of y equals the square root of x times the quantity 2x plus 1 cubed. This function is a product of two parts, so we will use the product rule. First, we identify our two functions, u and v. Let u equal the square root of x, which we'll write as x to the power of 1/2. Let v equal the quantity 2x plus 1 cubed. Next, we find the derivatives of u and v. The derivative of u prime, is 1/2 x to the power of negative 1/2. To find the derivative of v prime, we need to use the chain rule. The derivative of the outer function is 3 times the quantity 2x plus 1 squared. The derivative of the inner function is 2. So v prime is 6 times the quantity 2x plus 1 squared. Now we have all the pieces for the product rule. Dix equals u prime v plus v prime. Substituting our expressions, we get 1/2 x to the power of negative 1/2 times the quantity 2 plus 1 cubed plus x to the power of 1/2 times 6 times the quantity 2x plus 1 squared. This is a correct derivative, but we can often simplify it by factoring out common terms. Both terms have a factor of x to the power of negative 1/2 and a factor of 2x plus 1 squared. Factoring these out leaves us with 1/2 times the quantity 2x plus 1 plus 6x. Simplifying the expression in the brackets gives us 7x plus 1/2. So the simplified derivative is x to the power of negative 1/2 times the quantity 2x plus 1 squared times the quantity 7x plus 1/2. Our final rule for today is the quotient rule. This rule is used to differentiate a function that is the ratio of two other functions. Suppose we have a function q of x that is the quotient of two functions, u of x divided by v of x. Similar to the product rule, the derivative of a quotient is not simply the quotient of the derivatives. We need a specific formula. The derivative of q of x is given by the derivative of the numerator, u prime of x, times the denominator, v of x, minus the numerator, u of x, times the derivative of the denominator, v prime of x, all divided by the denominator squared, v of x squared. A common mnemonic to remember this is low d high minus high to low over low squared. Here, low refers to the denominator v, high refers to the numerator u, and d means to differentiate. Let's apply this rule to an example. Let's find the derivative of y equals the quantity 1 plus 3x, divided by the quantity x squared plus 1. This is a quotient, so we will use the quotient rule. First, we identify the numerator u and the denominator v. Let u equal 1 plus 3x and let v equal x squared plus 1. Next, we find their derivatives. The derivative of u prime is 3. The derivative of v prime is 2. Now we substitute these into the quotient rule formula. Dex equals u prime v minus u v prime, all over v squared. This gives us 3 times the quantity x squared plus 1, minus the quantity 1 plus 3x times 2x, all divided by the quantity x squared plus 1 squared. The final step is to expand the numerator and simplify. Expanding the numerator gives 3x squared plus 3, minus 2x minus 6x squared. Combining like terms, we get negative 3x squared minus 2x plus 3. So the final derivative is negative 3x squared minus 2x plus 3, all over the quantity x squared plus 1 squared. Let's look at a more complex quotient rule problem that also requires the chain rule. We want to find the derivative of y equals the square root of x, divided by the quantity 1 minus 2x squared. First, we rewrite the functions with exponents. Let u equal x to the power of 1/2, and let v equal the quantity 1 minus 2x squared. Now we find their derivatives. U prime is straightforward. U prime is 1/2 x to the power of negative 1/2. For v prime, we must use the chain rule. The derivative of the outer function is 2 times the quantity 1 minus 2x. The derivative of the inner function is negative 2. Multiplying these gives v prime equals negative 4 times the quantity 1 minus 2x. Now we apply the quotient rule. Die Laplace dt equals u prime v minus uv prime all over v squared. Substituting our expressions, we get 1/2 x to the power of negative 1/2 times the quantity 1 minus 2x squared minus x to the power of 1/2 times negative 4 times the quantity 1 minus 2x, all divided by the quantity 1 minus 2x to the power of 4. Let's simplify this expression. We can factor out common terms from the numerator. The common factors are x to the power of negative 1/2 and 1 minus 2x. Factoring these out, we are left with 1/2 times the quantity 1 minus 2x plus 4x. Simplifying the bracketed term gives 3x plus 1/2. So the derivative is x to the power of negative 1/2 times the quantity 1 minus 2x times the quantity 3x plus 1/2, all over the quantity 1 minus 2x to the power of 4. We can simplify this further by canceling a term of 1 minus 2x from the numerator and denominator, and rewriting x to the power of negative 1/2 as 1 over the square root of x. This gives us the final simplified derivative, 6x plus 1, divided by 2 times the square root of x, times the quantity 1 minus 2x cubed. Let's recap what we've learned. We've covered 3 essential differentiation rules. First, the chain rule, for differentiating composite functions. Second, the product rule, for differentiating a product of 2 functions. And third, the quotient rule, for differentiating a ratio of 2 functions. Mastering these rules is crucial for success in IB Mathematics AAEHL. They are the building blocks for more advanced calculus topics. Now, let's test your understanding with some practice questions. I will provide the questions, and then we will go through the fully worked solutions. Here are 5 practice questions. I encourage you to pause the video and attempt them on your own before watching the solutions. Question 1. Differentiate y equals the quantity 3x squared minus 5x, all to the power of 4. Question 2. Find the derivative of f of x equals x cubed times the square root of 2x plus 1. Question 3. Differentiate g of x equals the quantity x squared plus 1, divided by the quantity 2x minus 3. Question 4. Find the gradient of the tangent to the curve y equals 1 over the quantity 4x plus 1 cubed at the point where x equals 0. And question 5. If y equals x squared times the quantity x minus 2 cubed, find the values of x for which dx equals 0. Take your time and remember to show all your steps. When you're ready, continue the video for the solutions. Welcome back. Let's go through the solutions together, starting with question 1. We need to differentiate y equals the quantity 3x squared minus 5x, all to the power of 4. This is a composite function, so we use the chain rule. Let u equal the inner function, 3x squared minus 5, then y equals u to the power of 4. Now we find the derivatives. Du is 4u cubed, and du x is 6x minus 5. Applying the chain rule, dx equals du times du d. This gives us 4u cubed times the quantity 6x minus 5. Substituting u back in, we get our final answer. 4 times the quantity 3x squared minus 5x cubed, times the quantity 6x minus 5. Now for question 2. We need to find the derivative of f of x equals x cubed times the square root of 2x plus 1. This is a product of 2 functions, so we use the product rule. First, let's rewrite the square root as a power. F of x equals x cubed times the quantity 2x plus 1 to the power of 1/2. Now we identify u and v. Let u equal x cubed and let v equal the quantity 2x plus 1 to the power of 1/2. Next, we find their derivatives. U prime is 3x squared. For v prime, we use the chain rule. The derivative of the outer function is 1/2 times the quantity 2x plus 1 to the power of negative 1/2. The derivative of the inner function is 2. Multiplying these gives v prime equals the quantity 2x plus 1 to the power of negative 1/2. Applying the product rule, f prime of x equals u prime v plus uv prime. This gives us 3x squared times the square root of 2x plus 1 plus x cubed divided by the square root of 2x plus 1. To simplify, we can find a common denominator. Multiplying the first term by the square root of 2x plus 1 over itself, we get 3x squared times the quantity 2x plus 1 plus x cubed, all over the square root of 2x plus 1. Expanding the numerator gives 6x cubed plus 3x squared plus x cubed. which simplifies to 7x cubed plus 3x squared. Factoring out x squared, we get our final answer. X squared times the quantity 7x plus 3, all over the square root of 2x plus 1. Let's tackle question 3. We need to differentiate g of x equals the quantity x squared plus 1, divided by the quantity 2x minus 3. This is a quotient, so we use the quotient rule. Let u equal the numerator, x squared plus 1, and let v equal the denominator, 2x minus 3. Now we find their derivatives. U prime is 2x and v prime is 2. Applying the quotient rule, g prime of x equals u prime v minus u v prime, all over v squared. This gives us 2x times the quantity 2x minus 3, minus the quantity x squared plus 1 times 2, all divided by the quantity 2x minus 3 squared. Finally, we expand and simplify the numerator. Expanding gives 4x squared minus 6 minus 2x squared minus 2. Combining like terms, we get 2x squared minus 6x minus 2. So the final derivative is 2x squared minus 6x minus 2, all over the quantity 2x minus 3 squared. Let's move on to question 4. We need to find the gradient of the tangent to the curve y equals 1 over the quantity 4x plus 1 cubed at the point where x equals 0. The gradient of the tangent is the value of the derivative at that point. First, let's rewrite the function. I equals the quantity 4x plus 1 to the power of negative 3. This is a composite function, so we use the chain rule. Let u equal 4x plus 1. Then y equals u to the power of negative 3. Now we find the derivatives. Die slash do is negative 3u to the power of negative 4, and do dx is 4. Applying the chain rule, die slash dx equals die slash do times do d. This gives us negative 3u to the power of negative 4 times 4, which simplifies to negative 12u to the power of negative 4. Substituting u back in, we get Iowa dx equals negative 12 times the quantity 4x plus 1 to the power of negative 4. Now we need to find the gradient at x equals 0. We substitute 0 into our derivative. At x equals 0, dx is negative 12 times the quantity 4 times 0 plus 1 to the power of negative 4. This simplifies to negative 12 times 1 to the power of negative 4, which is just negative 12. So the gradient of the tangent at x equals 0 is negative 12. Finally, let's solve question 5. If y equals x squared times the quantity x minus 2 cubed, we need to find the values of x for which die dx equals 0. This is a product, so we use the product rule. Let u equal x squared and let v equal the quantity x minus 2 cubed. Now we find their derivatives. U prime is 2x. For v prime, we use the chain rule. The derivative of the outer function is 3 times the quantity x minus 2 squared. The derivative of the inner function is 1, so v prime is 3 times the quantity x minus 2 squared. Applying the product rule, die or dx equals u prime v plus uv prime. This gives us 2x times the quantity x minus 2 cubed plus x squared times 3 times the quantity x minus 2 squared. We need to find when this derivative is equal to 0. Let's factor the expression. We can factor out 2x and the quantity x minus 2 squared. This leaves us with the quantity x minus 2 plus 3x. Simplifying the bracketed term gives 4x minus 2. So, die dx equals 2x times the quantity x minus 2 squared times the quantity 4x minus 2. Now we set the derivative equal to 0 and solve for x. Setting the factored expression to 0, we see that the derivative is 0 when x equals 0, or when x equals 2, or when x equals 4, 5. These are the x values where the tangent to the curve is horizontal. That concludes our session on the chain, product, and quotient rules. We have successfully met our learning objectives. You are now equipped to apply these powerful rules to differentiate a wide variety of functions, a skill that is fundamental to your IB Mathematics AA/HL studies. Remember, practice is key to mastering these techniques. Continue working through problems to build your confidence and proficiency. Thank you for watching.